All right. So let's start talking about Rust at CppCon. Okay, so basically what we have here is Hello World in Rust. They have a nice function that allows you to print a line. And one of the nice things about Rust is that it supports UTF-8 natively, I believe. And that allows us to have different characters that aren't part of the ASCII character set. But that may lead to things getting malformed. So there are also Unicode escapes in Rust string literals, and we do that by using \u, and then in braces we are allowed to have between 1 and 6 hexadecimal digits. And we're going to implement a short parser for Unicode characters in C++ using ranges. So the first way we might try it is using a raw loop. And so we're going to set out a few expectations. These are all pseudo contracts that allow us to say, look, if this isn't going to, if we haven't met the preconditions, then we're either going to crash or just the optimizer is going to take advantage of the fact that this algorithm doesn't acknowledge that you can pass things in incorrectly. And so we expect there are going to be a minimum of 5 characters because \u, open curly, and close curly are all characters that are going to be there, and we need to have at least 1 digit, so that's a minimum of 5 characters. We're also going to expect that the escape starts with \u, open curly, and ends with a close curly. And finally, we want to assert that there's also going to be exactly 1 close curly, because that's important as well. And so now for the actual algorithm, what we're going to do is we're going to start from the 4th character onwards, because we don't have to care about \u, open curly, and we're going to continue until we reach the end of the range. And then what we're going to do is we're going to check to make sure that we have a hexadecimal digit. And if it isn't a hexadecimal digit, or we've reached something beyond the size of what we're expecting, we're going to simply return false, otherwise we return true. But what's wrong with this code? Don't like the constants that are 6 and 4, Ben? The last character is going to be a curly, yes. So those are 2 things that are problematic. The third thing is that this was a talk that was promising ranges, and this uses 0 ranges. So let's move on to something that is a little bit more algorithmic, and we again have our expectations. And what we're going to do here is we're going to replace that exactly 1R curly with an algorithm, so that way we don't have to continually reinvent the wheel. And so we're expressing our intention. We are counting the number of closed curlies and saying we expect 1 of them. And then we're going to find the first curly, move on past that one because we don't actually want to consider that. And then we want to state that we're going to consider things up until the end of, until we reach the closed curly, which is going to point out which is going to fix the problem that Ben identified. And then what we're going to do is we're going to check that the number of characters between there is between 1 and 6, and that all of them are hexadecimal digits. But again, this is still verbose, so let's have a third attempt. And this is going to start leveraging things from the ranges library. The first thing we do is, unlike with this one here where we're using a size function, we're going to change to a distance, which is a bit more expressive. And then we're going to, on line 6, use the count algorithm that is range-based instead of iterator-based. Otherwise, it's still the same at the moment. We're then going to kind of just simplify the code that was there and wrap it inside a subrange, which is a way of wrapping iterators into something that resembles a range. And then we'll use that to, again, complete the same operation. And this is how you would implement the second attempt using C++ 20 ranges, but we can go a little bit further again, and we'll be able to use range adapters, which allow us to express things even more clearly. So we start with two lambdas, one that says not open brace and one that says not closed brace. That's just expressing our intentions in words. And then what we do is we provide a range called Unicode that basically says that until we reach an open curly, we don't want to consider any characters, we just want to discount these. And then we want to discount the open curly and continue acknowledging elements in the range until we reach a closed brace. And then the algorithm is more or less the same as it was before. We're just checking that there are at most six characters and that they're all hexadecimal digits. And so this is an example use case of using ranges. Before I continue, I'd just like to point out that this is a personal presentation and any views, opinions, or statements represented in this presentation are personal and they belong solely to me, the presentation owner, and do not represent those people, institutions, or organizations that the owner may not be associated, may or may not be associated with in a professional or personal capacity unless explicitly stated. Yes, that was a lot. There are related talks. So generic programming by Sean Parent back at Pacific++ last year was kind of what inspired me to give this talk in this format. Then there were a few CppCon talks. Can I get a show of hands, please? Who has seen a Rangers talk before? Okay, that's a fair amount of the room. Can I get hands swapped? So if you haven't seen a Rangers talk before, can I get a show of hands, please? Okay, so this talk is not going to be talking about we're not going to be talking about how to use ranges in this double session. It's going to strictly be about understanding ranges and implementing them. So what we're going to cover is we're going to understand the basis behind what ranges are in this first hour, and we're going to motivate the need for understanding what a range is and how we move with ranges to actually implement one. And in the second hour, we're actually going to spend some time implementing a range adapter. If you have any questions, you're free to interrupt me at any point. I do ask that you use the microphone in the middle of the room, so that way everything's caught on camera and so that way everyone can hear you. And finally, we're going to be using a few terms, so I figured that it would be important to brief you on that. First of all, if you see ranges, it's going to refer to the namespace std ranges. The namespace views refers to std views, and the namespace CppCon is the content that you'll find in namespace ranges or namespace views, but it's slightly different. I've omitted something. For example, projection is something that everyone's been talking about when it comes to ranges in this year. To keep things a little bit more focused, I have omitted projections. So instead of putting this stuff in the ranges namespace, I'm putting it in the CppCon namespace to help you work out where things are different from what's in the standard. Okay, are there any questions so far? I see none. All right, let's start off with a simple definition, and that is that a range is an ordered sequence of elements with a designated start and a rule for finishing. An example of a range is a vector, which with two elements, hello, CppCon, and a string view. That's also a range. For the vector, the designated start is hello, and the rule for finishing is when there are no more elements left. The designated start for the string view is h, and the rule for finishing is when there are no more characters left. All of the natural numbers, integers, rational numbers, and real numbers can form a range as well. So, for example, the natural numbers have a designated start of 0, and the rule for finishing is that it just doesn't end. For integers, we could say that a designated start is -2, and the rule for finishing is that it is +6. And then you can make similar sorts of points for rationals and real numbers. Unfortunately, complex numbers don't fall into this because they don't have an ordered sequence. Ordered sequence means something comes before something else. It doesn't necessarily mean that it's lexicographically less. For example, hello is going to compare lexicographically greater than CppCon, yet it comes before CppCon. So if we impose a partial order on the complex numbers where the real part is compared first and the imaginary part is compared second, then we can say that we have a form of range for complex numbers. And finally, we also have streams, which form a sequence because you can get things from an input stream repeatedly until there's nothing left in the stream, or you reach a bad format. For example, we're reading in integers in this example, and if you pass in something that isn't an integer, then the stream will suddenly be in a fail state. Are there any questions about the definition, this hand-wavy definition of what a range is? I see a question at the front.
You say order didn't define it. Some of your examples are not well ordered.
Yes, so the point is that I didn't particularly define what I meant by ordered. What I mean is that an element in the range comes before another element, and it will always come before that. That's why the natural numbers are naturally ordered. 0 comes before 1, before 2, before 3, but the complex numbers aren't ordered unless we impose a partial order. Does that help answer the point? We'll come back to this in a much more rigorous detail in a little bit. Okay, so there is an algorithm on screen, and it is a linear search. Essentially, we're just going to be iterating over everything until we find something, and then we return the position of that. This is a linear search for a vector, and this is a linear search for an array, and this is a linear search for a raw array. And this is a linear search for a pointer to an array. Does anyone see a common theme here? Can I show of hands? Who thinks that these are basically the same with a different type? Okay, so one possible solution to that is that we could use span. And span allows us to say that if there's a contiguous sequence of elements, then we can wrap them inside this pointer to the first element and add a size. And so now we've just solved this problem. But there is a problem with this solution. What is that problem? Well, sorry? It only works on finite sequences, and it only works on contiguous sequences. So for dec, for example, is not a contiguous sequence, and that means that span is just going to fall over here. So we need to have another overload for the dec. And for linked lists, doubly linked lists. And so let's take a step back, look at two algorithms, just compare them, see what's similar, see what's different. In both of these, we have a start point, and then we have a rule for finishing. So the rule for finishing for the span-based find is that we have a size that we're going to be reaching, and in the case of the linked list one, we're going to be saying, well, when the head is now null, we are going to stop. Then we have a way of moving forward to a successor element, or the next element in the range. And then what we do is we do a comparison and return a position based on what we've observed. And this is what a find would look like if we're streaming data. We're going to read something in, and we're going to continue reading until we either find something or the range is no longer readable. So there is a solution to all this. We can unify all this. Does anyone want to have a guess at what it might be? So I heard range in the front. The answer is iterators. And so without iterators, we have roughly, for every data structure and for every algorithm, we have roughly the product of the number of data structures and the number of algorithms as the number of algorithm implementations. Now I say roughly because we were able to remove a handful of those for contiguous ranges and just fold it into one span operation. But we were still bound to dec and linked lists and so on. But with iterators, we can replace that and say that if we have a number of data structures and a number of algorithms, we only need to implement around about the number of algorithms that exist. We definitely need to implement at minimum the number of algorithms that exist, but if we can make certain assumptions, then we can actually optimize, and that means there'll be slightly more algorithm implementations than actual algorithm names. Now, I know what you're thinking. You came here to learn about ranges, and I'm talking about iterators. I promise you there is a point to all of this. So, readable iterators are things that we can surprisingly read from. And so with span, we use an index, and with a linked list, we have a node that that's presumably a pointer. For an input iterator, which is an iterator that we can read from, it's an unspecified type. It's really just an implementation detail. For the actual operation, as I said before, it's a subscript operation or a dereferencing. These are all operations that are very similar. And for the successor, what you'll find is that we have we move by increasing the index or moving the head. And in the case of the iterator, we're just going to call a successor function. And comparison is slightly different, but again, we can unify it. The way we do that for span is to compare the current index against the size of the data. Of the span. For the linked list, we're checking that the head is not null. And in the input iterator case, what we're going to do is we're going to say that there's a thing called last that defines what the finishing rule is for the range, and we're going to compare the iterator first against the finishing rule last. We'll come back to that in just a moment. And so this is what usage of iterators looks like. You call ranges begin on some data, which is a vector of integers, and you also hand over something you get back from ranges end, and then you get back an iterator, and you use that. What you need to do is you need to compare that against the end of the range, so make sure that we're not going to accidentally be using something that doesn't exist. That's nonsensical. And then we can use the iterators to work out things. So we can work out how many elements are between the start point and where we are, and how many elements are between where we are and the end of the range. And this is what it looks like for lists. So almost nothing changes, just the type. And so this is what find looks like when we use iterators. What we do is we pass in an I, which is an iterator, an input iterator, and we have a value. And what we're going to do is with the indirect relation, we are going to be saying that we require that the what start first gives us back is comparable to the value type. But there is a problem with our design, and so here what we can do is we can compare a range that has a start point and a finishing rule where there are no more elements in the range. But what happens if we only want to search the first 10 elements? Well, we could do that by adding another overload where we provide what's called the iterator difference, which is, you may know that as the difference type. Or it's simply the number of, it's the type that allows us to represent how many elements are between two iterators. We can do that for find, but there is a slight problem. There's roughly 105 algorithms in the standard library at the moment, and there are many more that exist. We would have to provide an enormous number of algorithm implementations and overloads for this particular thing. It's not exactly a convenient solution. So what we can do is we can actually provide this thing called counted iterator, which allows us to provide an n, and then it will decrement until it reaches 0, and that's our finishing rule, that we have no more elements left from what we're considering. And so this is how its usage looks. The end is going to be a little bit ambiguous because there's no real finishing rule at this point. So what we could do is say that we have we could use a default constructed iterator, just as iStream iterator does in C++ 98 through to 17. But this is not particularly ideal because we now have to continually repeat the type, and that's a bit annoying. Not to mention, it's very verbose. So instead what we could do is we could use a default Sentinel. And this is a finishing rule. So Sentinel is a much more formal way of me describing what the rule for finishing is. Because we're going to say that with default Sentinel, it is simply the default operation. So, for example, if a stream goes bad or if our counted iterator goes to 0, then it's a common way of saying, yes, we're going to reach the end of this. And so the only change to our algorithm is that we add a new type called a Sentinel, and we change the type of last to that Sentinel. We say that S models a Sentinel for the input iterator I. And its usage is very much the same as before. And this is what it looks like with a list. And so now we can talk about ranges, because this is most definitely leading up to the definition of a range. And so here what we have is what we call an iStream view. And it allows us to describe an iStream as though it were a range. You'll notice that on lines 4 and 5, we're using result twice. We actually can't do this because the iterator we get back is what's called an input iterator, and that can only be used for single pass algorithms, meaning that the result is actually going to be trashed. So, no, it's not crossing out. Pretend that I've crossed out that line 5. Not sure why that happened. And so you'll have noticed that in all of these examples, we're using just the range. We're not saying begin and end anymore, which is similar to what we were talking about to begin with. And so the implementation for a range-based find is as follows. We simply we have what's called an input range, which is similar to an input iterator. And then we say that the indirect relation is applied to the iterator of R, and we get back this thing called a safe iterator, which essentially just makes sure that we don't accidentally have a dangling iterator, which is very dangerous. Now I want to focus on line number 5, which is defined as, we're calling the iterator-based find. And this is important because the definition of a range is simply that we can call ranges begin on the range R and ranges end on the range R. And what we're saying is that the return type of begin is going to be an iterator, and the return type of end is going to be a Sentinel for the thing we got back from begin. And so this is what the definition of a range is. We call an input range something that models the concept of a range, and its iterator type also models an input iterator. Finally, what you're familiar with is with vector and other types of containers is what's called a common range, where the iterator and the Sentinel are the same type. Are there any questions at this point? I can't see any. Okay, so it should all be coming together now, and so we're going to spend a few minutes looking at iterators, just to make sure that everyone understands the different kinds of iterators that we have and how we can move forward with building our range adapter. So Zach Lane wanted to see an algorithm called find last introduced into C++20. We unfortunately didn't get time to reviewing it in the library wording, so it didn't make it in. But here is an implementation of find last, which is like find. It's a linear search, but instead of find, which gives us the iterator to the first element, it provides an iterator to the last element that meets the value. So what we have to do is we have to cache the iterator. But you'll recall that I said that input iterators are only for single pass algorithms. We here have to do a multiple passes in order for this algorithm to actually make sense. Because if we have gone through 6 elements and the 5th element is the one that we're actually going to be returning, well, that's potentially been discarded. So we have to provide something that's a little bit more strict. And so that's called a forward iterator. And so if you took a photo of the previous slide, I recommend you delete that one, take a photo of this slide, because this one is actually a correct implementation. The previous one was incorrect. But otherwise, it is still the same. All we're doing is we're saying that you require something a little bit stronger, something that allows you to have multiple passes in your algorithm. So that way, we don't accidentally lose the data. This algorithm can be improved upon. So as I was saying earlier, we can provide optimizations. And so what we're doing here is we're passing through the algorithm, we're going forward and looking for something, caching it, and then moving on until we reach the end of the range, and we're going to return the last element that matched the value. But if we have a common range that happens to also be bidirectional, that is, we can move backwards, not just forwards, then we can actually just start at the end and continually move backward until we reach the end of until we reach the beginning of the range, and then that will automatically be the last element that matches the value. Are there any questions about that? Ben? So first is last and last is first in this case. And because yes, I swapped them around. It makes reading the algorithm a little bit easier than having to do it the other way around. Okay, so moving on, there is an algorithm called equal. And this allows us to check that two ranges values are equivalent for some given predicate for every element in the range. And we can do this by implementing it in terms of another algorithm called mismatch, which returns us an iterator to each range, and that tells us where the algorithms no longer meet. In this case, what we're saying is that we want to make sure that they're both at the end of their respective ranges. But we can optimize this a little bit further, and so if we use what's known as a size sentinel, we can say that we can compute the distance between the first element and the last element in constant time. And so that means that we can make this a constant time algorithm if the ranges are not actually the same size. Now, if you're familiar with iterators, you may be expecting me to talk about another particular category of iterators, but I'm going to take a bit of a digression and talk about writable iterator operations first, because it allows me to motivate the algorithms that will actually be important for talking about the next kind of iterator. And so it's very much the same, except that as a readable iterator in terms of syntax, except that we're also able to provide write operations. Are there any questions at this point? Okay, I see none. And so this is an example of a writable algorithm. So we have this thing called weakly incrementable, which means that we can basically just move to the next element. And indirectly copyable means that we can copy something from our input range into our output range. And so moving on from this, we have things known as permutations. And a permutation is something that can be rearranged. And a classic example of a rearrangement is reversing. Say we want to walk backwards. Well, what we can do here is we can reverse the range by simply taking all the elements and putting the first element in the last point and swapping them until we've got the range in a backwards fashion. There's another one called remove, and remove cops a bit of flack. It's an algorithm that what it does is it takes all the elements that meet a particular predicate and then allows us to do something with those by putting them at the back, and then we can remove them from the actual range by erasing them. But while this is a canonical usage of how we would use remove, it's not the only way. We can also copy them from a particular range to another range. So we can copy one range into this as well. And so now we've got, we were able to check that it's different. All right, so another kind of rearrangement, this is one that I actually want to talk about, is naive shuffle, or just shuffling in general. So let's say we have a fresh deck of cards and we want to shuffle them. We can provide a way of doing this by simply taking the current position and swapping it with someone else. And so this is what the algorithm looks like. Are there any questions about it? I see none. Okay, so I benchmarked it. And I used 5 million cards in my deck. And for a vector, it's roughly 30 milliseconds. For a deck, it's roughly 38 milliseconds. For a list, it's about 11.5 hours. And if I copy it from if I copy my list to a vector and shuffled it, then copied it back, it's about 70 milliseconds. So this shuffle algorithm, although it works for bidirectional ranges, isn't exactly the best, implementation. And so we can, if we have this thing called random access iterator, which allows us to make arbitrary steps in constant time instead of just single steps in constant time, then we're able to move forward a lot more easily. So what we have here is we're saying that we need to be able to permute the elements, and we require a random access iterator. And so what we're going to do is we're going to have a bit of setup. And then what we're going to do is we're going to iterate from what we're going to call the mid until we reach the end. And then what we're going to do is we're going to perform a swap with the elements, and we're going to do this in constant time. Are there any questions about that? Now, we can take arbitrary steps forward, we can take arbitrary steps backward in constant time, we can do comparisons, and this will all become more apparent once we reach the second half of this talk. Contiguous ranges are the final piece of the puzzle, and I don't have any algorithms that I can succinctly use as motivation for contiguous ranges. It's possible that they're usable in heterogeneous contexts, so I recommend taking a look at Gordon Brown's talks about SYCL to see more about heterogeneous contexts. Now, let's talk about having some integers in a range. This is one way we could do it. We could have eight elements in a vector. We could use a loop to fill them with 0, 1, 2, 3, 4, 5, 6, 7. Does anyone know an algorithm that could replace this? I see an answer in the front. Iota, yes. So we could do this. And unfortunately, the numeric algorithms were not rangified in C++20 for many good reasons. And so we're still using the C++11 iota. And so that will give us exactly the same result as before. This is not ideal though, because I could do a pop back, and that suddenly means that the range, which I was expecting to be of size 8, is now of size 7, and so there's been an intermediate change there. It'd be nice if we could actually do this all in one step. And so the way in which we could do this is to use an iota view. An iota view behaves similarly to the algorithm iota, but it behaves lazily, means that we have to actually invoke it. For example, we would need to call equal on this and then compare it against an array that would then lazily generate all of the elements between 0 and 8. And it's important to understand that although there's 0 and 8 here, 8 is not going to be a part of this. It's a half-open range, meaning that 8 is the end. Once we reach 8, we terminate. You don't get 8 back. Is anyone familiar with the Collatz conjecture? Okay. Is anyone in the room not familiar with the Collatz conjecture? Okay. So the Collatz conjecture is essentially an algorithm that I believe is still unsolved in mathematics. We're not sure if it terminates or not, but basically the rule is that you start with an integer greater than 0, and what you do is you continually apply this rule where if the algorithm is even, then you halve it. Otherwise, you triple it and add 1. And you continue to do that until you reach 0. And as I mentioned before, we're not sure if it actually terminates. And so what we can do is we can generate the individual elements of the Collatz conjecture using iota and then composing it with transform. So what we do here is we pass something that modifies the range, and then we transform that into the Collatz conjecture. And this kind of version of Iota is not bounded, which means that there isn't an end to it. It just goes on forever. And when I say forever, I literally mean until we exhaust the difference type, and then we reach undefined behavior. So a good way for us to actually to move on from this is to use what's known as take view. And take view allows us to specify a way of moving forward. So what we can do here is we can say that there are going to be at most 10 elements in this range. Are there any questions about that? I see a question. No, so the question was, is this all eagerly generated? The answer is no, this is not all eagerly generated. This is all lazily generated. And what we would need to do is we would need to provide something such as range is equal, and then provide something else there to generate every element on the fly. Are there any, does that answer the question? Okay. Are there any other questions? I don't see any. All right, so let's move forward, and let's talk about views in a little bit more detail. So the two that you may be familiar with are string view and span, and those two are the canonical things that we think of at first. But C++20 actually introduces a lot more views than that, and they're all inside the ranges namespace. And so empty view provides us with an empty range. It's useful when we want to say this range is empty, but we don't have any other way of doing that. Filter view allows us to take out elements that don't satisfy a given predicate. Drop while view allows us to discount elements until a particular condition is satisfied. We saw that one at the very start. There are a large number of views that are out there, just as Sean Parent has quoted Alex saying that there's a very large number of algorithms, and the STL is only a small survey of them. There are many ranges that are out there, and we only have a small survey of them both in the standard library and in the canonical library implementations. The canonical library implementations are Range v3, which is the oldest modern version of ranges, CMC STL2, which is an experimental version of ranges using concepts and GCC, and now MSVC actually, and NanoRange, which is an independently produced one that is very faithful to what's in the standard. Now, the definition of a view is that it's a range that also models the concept semi-regular, and we also have this Boolean called enable view. And enable view really just says that we have something that is pretty much, it's a view. Now, moving forward from that, on Twitter, I see a question. So the question is which views are in the views namespace and which ones are in the ranges namespace. So all the things that are, barring the ones that say stood on screen, which is string view and its friends, such as basic string view, everything that is suffixed with _view is in the ranges namespace, and then it has a related object that lives in the views namespace. So these are all types that live in the ranges namespace, but then we have objects, which I'll be getting to in the second half in quite some detail. So that does that answer the question, at least for now? It'll become much clearer once we reach the end of the second half. Are there any other questions? I see a question. Right, so the question is, what is the significance of enable view, and what does it mean? So I've only given a partial definition of what a view is. The full definition is these are the syntactic requirements of a view. There are semantic requirements as well. And the semantic requirements of a view are that it has a constant time copy operation, a constant time move operation, constant time assignment, and constant time destruction. That's the definition of a view, or the full definition of a view. Enable view allows us to either opt in or opt out depending on what you need to do so in the event that you don't actually meet those semantic requirements. Because you can meet all the syntactic requirements, but if you don't meet the semantic requirements, you shouldn't be modeling the concept view. And also, you're not modeling the concept view, and you should be opting out of that from a syntax point of view. Does that answer the question? Cool. Are there any, is there any confusion over what I just said? Because I get that may be a new notion. I see none. Oh, there is one, sorry. Sorry, you were right in the light there. Yeah. So the question was that I just noted that views need to be constant time copyable, and the question was, is it does that mean that views can't cache what? Sorry. Right. So just if they can't cache, and while many views don't need to cache, some views do actually need to cache, and they have certain rules on them that mean that we need to obey certain principles. And so I'll be covering that in just a moment. But some views do absolutely need to do some caching, and while we don't actually cover the caching in this particular session, that is an optimization opportunity that you can definitely leverage from this. It's just it would be too much to put on the slides. Does that answer the question? Cool. Are there any other questions? Didn't want to miss anyone. I don't see any. Okay, so a few weeks ago I decided to query what people were interested in seeing because that's important to understand. I promised that I would build a non-standard range because the ranges that we have in the standard have a formal specification. They're going to be in your standard libraries, hopefully very soon. And there are canonical implementations of all of these, possibly barring one. And I figured that it would be interesting to see something that may not actually be as straightforward. So the first one that I considered was slice view. And this is what an example of a slice view is. On screen, what we have is a slice between the elements 3 and 6, and so we only consider the elements in this particular bit of the range. And this is a slice between the elements of from position 4 and 8. And so this was one of the more popular range adapters that we could particularly implement. And I have just realized that I haven't actually explained what a range adapter is. A range adapter is something that something that takes a range, and that can be converted into a view, and then gives us back a view that has some transformative properties. For example, slice view will discount all the elements that come before the first position that we've specified, which is 4, and only consider things up until the 8th position, which means that we stop once we reach the 8th position. Are there any questions about that? I see a question in the view. So the point that Devere made was, why don't we just use take and drop? And that's how we implement it. So here what we have is a lambda. And in this lambda, what we're going to do is we're going to take two integrals, and we're going to make a point of saying that both d and t, so d is the number of elements that we want to discount, and t is the number of elements we want to consider. And what we're going to say is that both of them need to be positive, and d needs to be smaller than t. And then what we're going to do is we're going to drop the number of elements we're going to drop the first number of elements. We're going to discount them. They're not a part of it. And then we're going to take the difference. And the reason for that is because we want to say where the range stops, not just consider this number of elements. Question at the front. You mean this one? The question is, what is the return type? And the return type of this will be a bit complicated for me to explain in words. Sorry, what was the question? Right, so what it is what's called a closure, a range adapter closure. And we will get to that at the end of the next session. It's the very last thing we talk about in the entire session. But essentially what that is a way of storing all the lazy information before we actually have a range that we can adapt. So what we're saying here is we have a range adapter and we want to compose it with another range adapter, and we're going to return some unspecified type so that way we can work with it as we move forward. And then when we pipe a vector into this, it would then form some larger type that actually can then be actioned. And so, I see a question? So the return type is an unspecified type. A view is something such as filter view or take view, whereas in this particular case, it's something that's implementation specific, and it's related to what we get back. Yes, it is platonically a view, but type-wise, it is something that is view-related, but not actually a view. Does that make sense? On its own, no. It does not model view. It needs to have a bit more information to get that far. Are there any other questions? I see a question at the front. Is the slide title misleading? It's really just for consistency with the previous slice view slides. I would agree that it is slightly misleading, yes, because this should be views slice, or at least CppCon views slice. Building a slice view is something that's a bit more involved, but we don't need to do that in C++20 because we can make this lambda, and that serves for most of the purposes that we have, that we probably want. If you need the extra information, yes, you can go and build the remainder of the slice view. But for all the use cases that I can foresee, barring that special information, this is all you would need to do. I'm sorry, I can't hear you. Would you mind going to the mic, please? So the question is there a reason I keep using the word and instead of using ampersand, ampersand? And the reason for that is because I prefer to use the English spelt words in my code instead of using ampersand, ampersand, and the pipe and the exclamation mark wherever possible, because it makes reading concepts easier and makes things and helps things to flow a lot easier, in my opinion. It's something that's been possible since C++98, but it is something that's been very relatively hidden. People aren't particularly aware of it. Now, I've just noticed that the time check, it is, we have roughly 7 minutes left. Are there any questions before we press on? Okay, I see none. So the next one that I considered was stride view. And I promise you, this time around, the underscore view is not going to be misleading. So in this case, what we have here is a stride. And a stride of 1. And that means that we're going to consider every single element. We only move forward by 1 every time. A stride view where the stride is 2 means we skip every other element. And a stride view of size where the stride is 3 would mean that we only consider every third element. Are there any questions about this? All right, so I think here would be a good point to pause. And so I'd like to thank you for your time. And in this session, we should have covered enough for you to get a feel for what the underlying architecture of iterators are, so that way we can move forward and produce a range adapter, which will be considered in the next session. So thank you.